In this lecture, we will be discussing the heat of vaporization and how to estimate it. Now, as a reminder, the heat of vaporization is the enthalpy change. We typically write it as delta H hat vaporization, which is the enthalpy change going from a liquid to a vapor state. So we'll write that as delta HV minus delta HL. So we're transitioning from the enthalpy of a liquid, which is our initial condition, to the enthalpy of a vapor, which is our final condition. Now, vapors can hold more energy, and so typically this is always going to be actually, it's always going to be greater than zero. The vapor is going to be holding more energy than the liquid is at a particular set of conditions. The heat of vaporization is a function of temperature, which means that we will need to have a system of being able to know what the heat of vaporization is for changing process temperatures and conditions. Typically, the heat of vaporization is tabulated or measured. Actually, it's tabulated from measurements. And this is generally done at T is equal to the normal boiling point. And I'll call this TB. And this is the boiling point at 1 atmosphere pressure. And so this is just an easy and convenient way. So if you're going to go into the laboratory and you're going to measure the heat of vaporization, well, it makes sense just to do it at normal atmospheric conditions. And so this information is generally put into large-scale tables, but it's not practical to go about and measure the heat of vaporization at every possible temperature. And so it's on us as chemical engineers to know how we can estimate the heat of vaporization under different circumstances. If we take a relatively simple system where we have a stream of a saturated liquid going through some sort of a boiling unit and creating a saturated vapor, what we'll want to know is how much energy needs to be put into this process in order to effectively perform the calculation. So if we go to our energy balance, for an open and steady system, we have in is equal to out. So effectively all we're doing is we're figuring out how many streams are providing energy into the system, which is our boiler right here. And then we're going to be subtracting out all the streams that leave. So for the way that I've drawn this particular process, we have enthalpy entering in. Actually, we will not use the hat. We will just say enthalpy entering in this stream right here, and we have an out stream there. We have enthalpy entering in the form of energy Q based on how we've drawn the arrow going into the system, and the energy leaving the system is the total enthalpy out. Now we can also write this as the molar flow rate entering the system times by the specific enthalpy of the material entering the system plus Q, and the same for the outlet. Now what we want to do is we want to be able to figure out how we can actually solve this problem and figure out how much energy it will take to perform a particular chemical process. So what we're looking for is rearranging the equation to solve for 2, in which case we can move this to the other side of the equation, where we have n dot h hat out minus n dot h hat in, and oftentimes we write this in a more compact form, n dot delta h hat, where the delta h hat is h hat out minus h hat in. Now this is all relatively simple and straightforward if this is at pressure is equal to 1 atmosphere, in which case the delta H of vaporization in this particular example is going to be the same delta H as right here, because we're transitioning from a saturated liquid to a saturated vapor. Now if this pressure is not equal to 1 atmosphere, we need to come up with some different ways in order to estimate delta H of vaporization at any particular system temperature that we are going to be interested in, and that's going to be the main topic of this video lecture. the three approaches that we're going to discuss in order to estimate the heat of vaporization. The first one is using the Clausius-Clapeyron equation. The second approach is what I like to call the C sub P method, and I'll elaborate on that in a moment. And the third approach is to just estimate it. And for this we'll use the Watson correlation. So starting off, before we actually move into using the Clausius-Clapeyron equation, let's do a really quick recap on how pressure actually influences the heat of vaporization. So recall that boiling occurs when the vapor pressure, P star, is equal to the system pressure. If we were to vary the pressure of the system, and this is of course for a single phase system, this is for single component I mean. For a multi-component system we would have to use Raoult's law. Where we have YIP is equal to XIPI star of T. And this equation would have to be satisfied for every material in the system. So if the pressure is greater than 1 atmosphere, that would mean that the bubble or the dew temperature would have to be greater than the normal boiling point, which we'll call it T boil. If the pressure is less than 1 atmosphere, that means the T bubble or dew point would be less than T, the normal boiling point. So in this circumstances here then, the pressure influences the temperature, which then influences the delta H of vaporization. Now, moving on to the three methods to estimate the heat of vaporization. The first one is the Clausius-Clapeyron equation, which can be written as the natural log of the vapor pressure is equal to minus delta H hat of vaporization over RT plus B. Now we can rewrite this as minus delta H of V R. All I'm doing is regrouping how things are arranged, and we can see that this is very easily put into slope-intercept form. This is y equals mx plus b. So if we have access, and this is slope-intercept form, so if we have access to the vapor pressure as a function of temperature, it's really only a matter of plotting up the actual data, and we can have a means of estimating the heat of vaporization. So if we have access to the right data, we'll just plot ln of P star as a function of 1 over T, in which case we'll have some sort of a line or a curve near our temperature that we want to actually estimate the heat of vaporization. The slope m is going to equal minus delta H of vaporization over R. And this is kind of a brute force methodology in order to estimate what the heat of vaporization is. And this is actually how heat of vaporization is measured in the laboratory if you were to do it at some sort of an industrial lab. The second approach is what I call the C sub P method. And this one relies a lot on understanding the basic thermodynamics of enthalpy and state functions. So if we were to consider a phase diagram, this is going to be temperature, this is pressure. We have solid, liquid, and vapor. This line right here is for vapor-liquid equilibrium, the coexistence region. This is the critical point. And what we are interested in is the transition from a saturated liquid here going over to a saturated vapor over here at a, oh, my bad, this is a switch, this is pressure, and this is temperature, my bad. What we're interested in is if we have at T, the normal boiling point, this is corresponding to a pressure of 1 atmosphere. What we're interested in is this data point right here gives us the heat of vaporization, delta H vaporization at TB. This is typically tabulated. What we want to know is what is the heat of vaporization at some condition over here. And in order to notice why this is important, let's break it down and look at these plots a little more closely. So if we were to consider, if we were to plot the enthalpy of a fluid versus temperature or pressure, and actually going back one more slide, I want to mention one thing. At every point in space on this particular phase diagram, there is a particular enthalpy. So in this case here, we would have H hat of a liquid at whatever temperature and pressure we're at. Over here, we would have, H hat of the vapor at whatever temperature and pressure we're at. And so at every point in space on here, you can effectively think of this as some sort of a 3D plot or a contour plot where the elevation coming off of the page or off of the computer screen in this case corresponds to whatever the enthalpy is. So what we want to do is to look at the enthalpy as a function of pressure and a function of temperature to illustrate the heat of vaporization and why it's non-trivial to calculate potentially. If we are to plot the specific enthalpy as a function of the temperature, as we increase the temperature, we are going to be increasing the specific enthalpy until we reach the boiling point. Then we're going to have a discontinuity and furthered by an increase of the vapor. So down here we have liquid, up here we have vapor. The slope of this line corresponds to the specific heat of the liquid. The slope of this line corresponds to the specific heat of the vapor, and the difference here is the delta H of vaporization going from a vapor to a liquid or vice versa. You'll notice that I drew the slope a little steeper for the liquid than I did for the vapor, and that's generally because the C sub P of the liquid is greater than the C sub P of the vapor because there are more intermolecular bonds in the system. If we are to plot the specific specific enthalpy as a function of pressure, in this case I'll draw it in the opposite direction. We'll start off here with the liquid at high pressure. Try and draw this a straight line. The enthalpy is a very weak function of pressure, so I'm drawing these as flat lines. Once we reach a condition where P star of T is equal to P, we're going to vaporize. So we'll have a discontinuity in our plot, which is a straight line, and we will continue on this way here. We'll have H hat of the vapor, and here is the delta H of vaporization. So the height of this discontinuity between the heat of vaporization, between the enthalpy of the vapor and the enthalpy of the liquid is a function of temperature. So if we move to a different position along this vapor-liquid equilibrium curve here, the step change from transitioning from a liquid to a vapor is different in size, and that is the basis for why we need to calculate the heat of vaporization as a function of temperature. So using the heat of vaporization method, what we're going to do is we're going to look at an expanded version of the phase diagram to illustrate how we can go about this. Now if we draw here, this is the boiling point of this pure fluid. And then this would correspond to the pressure of 1 atmosphere. This value right here, the transition from a liquid to a vapor, we know as the delta H of vaporization at the normal boiling point. But if we want to know the heat of vaporization right here, generally we're going to have a saturated liquid and we want to transition to a saturated vapor. But we don't know how steep this cliff is right here. We don't know how big this step is going from the liquid to the vapor phase. So what we have to do is we kind of have to reroute ourselves to go through this data point here that we actually know the conditions. And we can do this relatively straightforward by calculating enthalpy changes. So the first step would be to go from our saturated liquid state here and start to transition from whatever the temperature and pressure are at this state over here to this condition. So here we're at some arbitrary pressure P and some arbitrary temperature T. So the first step is we would go the delta H going from the system pressure to 1 atmosphere. The next step would be to transition over here, and this would be the delta H going from the system temperature to the boiling point of the fluid. We would add in the heat of vaporization. We would calculate, oh, and this is actually for a liquid. Then we would have the delta H contribution going from the system pressure of normal pressure of 1 atmosphere to the actual system pressure, but this is for the vapor because we have vaporized it. And then finally, we go back to our state of interest, which is the saturated vapor state. And this, of course, is going to be delta H hat. Delta H going from the boiling point to the conditions of interest. So just because we don't know how big the step change is here going from the liquid to the vapor state. So we have to take this relatively convoluted path through a data point that we actually know what the size of that discontinuity is, which is the heat of vaporization. So for that, we have to introduce a series of delta H calculations. First, we go and depressurize the liquid to the conditions of 1 atmosphere pressure. In this case we have to pressurize to go for 1 atmosphere, how I've drawn it. Then we have to heat the liquid. Then we have to vaporize it under conditions where we have access to the experimental data. Then we have to depressurize the vapor and then cool the vapor. And this whole process could be repeated, but from the opposite direction. If we were up here, we would be doing the similar steps, but increasing and decreasing the temperature situation would be flipped. So writing this out, what we're ultimately interested in, just in case we've lost focus a little bit, we want to know what is the heat of vaporization at this unknown system temperature, and we've broken it down into several steps. The first step was the delta H change going from the system pressure to 1 atmosphere for a liquid. Now the enthalpy is very insensitive to pressure, so we're going to approximate this as a 0, plus the enthalpy change going from the system temperature to the boiling point temperature, again for the liquid. Then we're going to add in the heat of vaporization for at the normal boiling point, which is TB, plus the condition where we're going to change the pressure from 1 atmosphere to P, but this is for the vapor because we have since vaporized it. Again, for an ideal system, we're going to say that the heat of the delta H is not a function of pressure. And then finally, we have the last delta H going from the normal boiling point at 1 atmosphere to the actual system temperature. Again, this is for the vapor. So replacing, introducing C sub p into this process, we can write delta H, this term right here, the delta H going from T to TB, T to TB, as C sub p of the liquid dt plus the delta H of vaporization at the normal boiling point plus this last enthalpy contribution here, which is the integral going from TB to T, C sub p of the vapor dt. And this is what we can use to estimate the heat of vaporization at some arbitrary state. So this approach works perfectly well if T is greater than TB or if T is less than TB. All of the signs will work themselves out. If we switch the bounds of the units, you'll just have a positive term over here and a negative term over here, or a negative term here and a positive term here. So the same exact approach works regardless if we are above or below the normal boiling point. And finally, the last method that we'll discuss is to estimate it. And for this, we're going to use the Watson correlation. And this is just it's just basically an equation that relies on the notion of the law of corresponding states. And the law of corresponding states basically states that all materials or fluids will behave relatively the same based on their deviation from the critical point. So for the heat of vaporization at any arbitrary temperature T2 can be related to the heat of vaporization at some known temperature condition. In this case, we call it T1. This is generally going to be at TB, which is going to be the boiling point. Here, the equation, I'll just write it out. This Tc is equal to the critical temperature. And this is the equation that you would need to estimate the heat of vaporization. So as the temperature T2 gets farther and farther away from T1, this correlation is going to be increasingly poor. There is one other interesting piece of information to point out on this particular equation, is that as T2 gets closer to the critical temperature, we can see that the heat of vaporization goes to 0. And this is because at the critical point and above the critical point, there is no difference between a vapor and a liquid, so it makes sense that there should be no allowable heat of vaporization. And this equation does indeed capture that phenomena. So this is 3 different approaches that we can use to estimate the heat of vaporization. This approach, or these methodologies, are very necessary when we're trying to perform energy balances, especially on flash separators, which is a topic for another video.